Welcome to the Deep Dive. We're the show that, well, tries to cut through all the noise and really get to the heart of complex topics. Today, we're looking under the hood of generative AI. You know, how these incredibly powerful models actually make sense of the massive amount of information out there. We're going to focus on two core components that are absolutely critical: embeddings and vector databases.
That's the plan. And our goal here isn't just to talk about these things. We want to distill these pretty technical AI and machine learning concepts, make them clear, practical, but without sacrificing the depth. So hopefully it's understandable for anyone listening, but also detailed enough that, someone with the right technical background could actually take these ideas and run with them, bridging that theory-practice gap.
Okay, let's start right at the beginning.
Mm.
The big problem, fundamentally, is that computers think in numbers, right? They don't inherently get human language or images or sounds like we do. So how on earth do we translate, say, the meaning of a sentence or the content of a picture into a format that a machine can actually process meaningfully?
Yeah, that's the million-dollar question. And the answer really revolves around embeddings. Think of embeddings as the key translator. They are essentially number-based representations of data. That's the core idea. They take something we understand, like a word or maybe a whole paragraph or even an image, and turn it into a vector. And a vector is just, well, a list of numbers.
A list of numbers. So if I think about the word apple, the computer isn't seeing AKPLE. It's seeing a string of numbers, like, I don't know, 0.1, 0.9, area 0.4, and so on.
Exactly like that. Each number in that list, that vector, it captures some aspect, some feature of that word's meaning, or maybe its relationship to other words. And here's the really cool part. Words that mean similar things end up with very similar vectors, numerically speaking. So cat and dog, because they're both common pets, both animals, their embeddings will be numerically close. Same for, say, car and train, both vehicles, so their vectors cluster together. This closeness in this high-dimensional number space, that is the computer's understanding of semantic similarity. It's like a map of meaning built with numbers.
A map of meaning. I like that. And these vectors, these embeddings, they aren't just random numbers. They're generated by really powerful AI models, right? Like the ones from OpenAI or Hugging Face, trained on just immense data sets. The source material even mentions specific models, like OpenAI's text embeddings at AI002. That one creates vectors with 1,536 dimensions for text. That sounds incredibly detailed for just one piece of text.
It is, and that high dimensionality allows for capturing really subtle nuances in meaning and context. But, okay, let's say we've done that. We've turned all our data, text, images, whatever, into these rich numerical vectors. Now what? Where do we put potentially billions of these things? And more importantly, how do we find the right ones later, quickly and efficiently? You can't just scroll through billions of number lists.
Yeah, that sounds like finding a needle in a haystack. But the haystack is the size of a planet, and the needle is also a number. A standard database search for keywords wouldn't work here, would it?
Not at all. Keyword search looks for exact matches. Here, we need to search for similarity in meaning based on those vector numbers. And that's precisely why we have vector databases. These are systems specifically built to store and, crucially, search embeddings efficiently. They don't just store the vectors, they organize them. They use clever mathematical techniques, things like cosine similarity or Euclidean distance, to calculate how close two vectors are in that meaning map.
So if I search for something like ideas for a sunny vacation, it wouldn't just find documents with those exact words. It might find things about tropical beach getaways or warm weather holidays because the meaning vectors are close.
Precisely, that's the power. And to do this fast, especially with huge data sets, they use smart indexing techniques. Think of methods like HNSW, that stands for Hierarchical Navigable Small World, or IVF, Inverted File Index. These methods essentially pre-organize the vectors, maybe grouping similar ones or building like a multi-level index. This drastically cuts down the search time because you're not comparing your query to every single vector. They also rely heavily on something called approximate nearest neighbor algorithms, or ANN. Finding the absolute mathematically perfect nearest neighbor in such high dimensions can be very slow. ANN finds extremely close neighbors very, very quickly. It's a trade-off, but a very effective one for balancing speed and accuracy. This kind of semantic context-aware search it's way beyond what traditional databases can handle at scale. You see names like Pinecone, FAISS, Weaviate, Milvus, pgvector popping up all the time now. These are the tools built for this job.
Okay, this is starting to click. Embeddings turn meaning into numbers. Vector databases store and search those numbers based on meaning. And this combination, this system, seems absolutely essential for making generative AI more useful in the real world. Let's talk about retrieval augmented generation, or RAG. This sounds like the mechanism that lets AI models pull in current specific information rather than just relying on what they were trained on months or years ago.
Exactly. RAG is a game changer. The core idea is simple but powerful. Before the large language model, LLM, generates an answer, it first retrieves relevant information from an external knowledge base. That knowledge base is often powered by embeddings and a vector database. This helps the LLM provide answers that are more accurate, up-to-date, and grounded in specific facts. It's a key technique to combat hallucinations, when the AI just confidently makes stuff up because it doesn't actually know the answer. Now, when you want to build RAG systems that handle multiple types of data, text, images, audio, video, what we call multimodal RAG, there are, broadly speaking, three main ways to architect it. Each has its pros and cons. First, you could try to use a common embedding space. The idea here is to have a single powerful model, maybe something like CLAP, which understands both images and text that maps all your different data types into the same numerical vector space. The pro, it sounds simpler, right? One space for everything. The con, though, is that finding or training a single model that's equally good at deeply understanding, say, medical x-rays, financial reports, and casual conversation is really, really hard. It often struggles with diverse or specialized data types. Okay, second approach. You could build n-parallel retrieval pipelines, basically a separate system for each data type. One pipeline searches text, another searches images, another searches audio transcripts, and so on. The upside. Initial data loading or ingestion can be simpler because you handle each type separately. The downside. You retrieve potentially relevant bits from all these different pipelines, and then you have to feed all that raw, diverse information to the LLM. This massively increases the amount of context the LLM needs to process. We call this the token count. That means higher costs, slower responses, and you need a really capable, usually very large LLM that can effectively synthesize insights across these very different formats. It's kind of a brute force method. Which brings us to the third way, which is often the most practical and flexible. Grounding in a common modality, and usually that common modality is text. Here, the strategy is to convert the key information from all your different sources, images, videos, audio, PDFs, into text first. Then you embed and index that text. The big advantage is that it unifies everything into a format that today's best LLMs are fantastic at handling. Search becomes simpler, generation is more streamlined, and you can tune models more effectively. The main drawback is you have a one-time cost and effort to do that conversion during ingestion, and you need to be careful because the conversion process can sometimes be lossy. You might lose some nuance translating, say, a complex image purely into text. But overall, for many real-world applications needing reliable RAG, grounding everything in text provides a really solid foundation.
That text grounding approach sounds very pragmatic. Get everything into the language the LLM understands best. Let's make this concrete. I often find myself skipping through long video recordings, lectures, meetings, tutorials. It feels like a jumble of audio and changing visuals. How would you even begin to apply RAG to something as complex and dynamic as video? What makes video so tough for AI?
That's a perfect example, and video is challenging. Why? Well, several reasons. Videos vary wildly structured tutorials versus, say, chaotic meeting recordings. Information is split across audio tracks and visual frames, and the sheer data volume is immense, like you said, 60 frames per second. That's 3,600 images per minute. For the kind of use case you mentioned, video explainers, lectures were usually interested in the informational content, the spoken words, the things shown on screen, rather than, say, subtle emotional cues or complex physical actions across many frames. So the process typically starts with the audio ingestion. We need to get the spoken words out. We use an automatic speech recognition or ASR pipeline, something like NVIDIA's Parakeet model, for example. This takes the audio track and transcribes it into text, crucially providing word-level timestamps alongside the text. That timing information is vital later.
Okay, so you get the transcript and timestamps, makes sense. But what about the visuals? Processing 3,600 frames a minute still sounds computationally insane and probably unnecessary if someone's just talking over a static slide for a while.
Exactly. It's overkill and inefficient. So the first step for video ingestion is to downsample. Maybe we only look at, say, 4 frames per second instead of 60. That immediately cuts it down to 240 frames per minute. Still a lot, but better. But we need to be smarter than just taking evenly spaced frames. We want the key frames, the ones where important visual information changes. How do we find those? Well, it's a multi-step process. First, we often chapterize the video. We detect shot boundaries when the camera cut happens. This gives us logical segments. Then, within each segment or chapter, we look for key clips or moments of significant visual change. We can do this by comparing frames using something like the Structural Similarity Index, SMM. We're looking for frames where the visual content is suddenly quite different from the previous one. Maybe a new slide appeared. That's a potential start frame. Then we look for where it stabilizes again. After identifying potential keyframes within these clips, we filter them. We throw out blurry frames, get rid of obvious duplicates, and critically, we often select frames based on entropy. High entropy suggests more visual information or complexity, like a detailed diagram or text on screen, not just a blank wall. This whole intelligent filtering process can take us from thousands of frames per minute down to maybe just 40 or 50 really information-rich keyframes.
Wow, okay. That's a dramatic reduction, focusing only on the visually significant moments. So you have these keyframes identified. What's next? How do you get the information out of those frames?
This is where vision language models, VLMs, come in. We use a powerful VLM, maybe something like the Llama 3 VLM in INEO, and we feed it these keyframes. We ask the VLM to do two main things for each frame. First, transcribe any visible text, like text on a slide or labels on a diagram. Second, generate a semantic description of what's actually in the frame, what's being shown, what's the context. Now we have text from the audio via ASR and text from the key visual frames via VLM. The crucial next step is blending this information. We use the timestamps, word level from audio, frame level from video to correlate everything. A common approach is to work at the scene or chapter level. We take the audio transcript for that scene, and then we append the text descriptions generated from the keyframes that fall within that scene's timestamps. You get a richer text block describing that part of the video. Now, sometimes the speaker might be describing exactly what's on the slide, creating redundancy. So an optimization step here can be to use another, perhaps smaller LLM during this ingestion phase. Its job is just to read the combined audio and visual text for a scene and create a more concise, less redundant summary. This saves on tokens later during actual retrieval.
Right, you're essentially creating this dense, time-coded, text-based representation of the entire video's content, pulling from both audio and visuals. Smart. So when you have this unified text, what happens?
Now we're ready to set up the retriever. This coherent text description of the video gets broken down into manageable chunks. Each chunk is tagged with metadata critically, the original source video name, and the precise start and end timestamps for that chunk's content. Then, an embedding model like the ADA002 we mentioned earlier calculates the numerical embedding vector for each chunk. And finally, these embeddings, along with their text content and that crucial timestamp metadata, are stored in our vector database. And that brings us to the payoff: generating answers. A user asks a question like, what did the presenter say about org-ag architectures? The system takes the user's question, embeds it into a vector. The vector database then searches for and retrieves the text chunks from the video data whose embeddings are most similar to the question's embedding. Often, there's a quick re-ranking step here, maybe using a different model, just to put the absolute most relevant chunks right at the top. These top-ranked, highly relevant text chunks, along with their metadata, are then passed to the main LLM as context. The LLM uses this specific context pulled directly from the video content to generate a concise, accurate answer. And because we kept the metadata, the system can say, here's the answer, and you can find this discussed in video X around the 15.3D mark.
That is incredibly powerful. You're literally enabling a conversation with video content, finding specific moments, getting answers grounded in the actual source material. I can see this being revolutionary for education, for analyzing meeting archives, even for reviewing security footage. It unlocks so much previously inaccessible information. Okay, so we've seen how embeddings and vector databases work together, especially in sophisticated applications like RG for video. Let's bring back to someone starting a project. They need a vector database. How do they choose? You mentioned Pinecone, FAISS, PG Vector. Let's compare them practically, maybe for that semantic search chatbot scenario.
Absolutely. Choosing the right tool depends heavily on your specific needs, scale, budget, and technical expertise. Let's look at those three. Pinecone first. It's a fully managed cloud service, big pro. It's generally very easy to get started with. You sign up, get an API key, and start pushing vectors. They handle the infrastructure, scaling, uptime, all that stuff. It's built for scale, millions, even billions of vectors. Great performance. And they usually provide a similarity score from 0 to 1, where higher means more similar, which is quite intuitive. The main con: it's a commercial service, so it costs money, although they do have a free tier for small projects. For a serious application, say 50,000 daily users generating maybe 1.5 million vectors a month, you might be looking at around $70 a month for a standard plan holding 5 million vectors. It's a cost factor.
Okay, so Pinecone is the easy-to-use, scalable, but potentially pricier managed option. What about FAISS? You mentioned it was different.
FAISS, Facebook AI Similarity Search, is quite different indeed. It's an open source library, not a managed database service. It primarily works in memory. Its strength is speed. It's incredibly fast for similarity search, especially if you can fit your index in RAM, the big drawbacks. Because it's in memory, your index size is limited by your available RAM, which can get expensive for very large datasets. Also, FAISS itself is just the search library. It doesn't inherently store metadata alongside the vectors. You usually need to build something around it, maybe use another database to store the actual text or links associated with each vector, or use a framework like LangChain that wraps faces and handles metadata. Scalability is basically limited to how big a machine you can afford. And note its similarity score convention. Lower scores mean closer vectors, the opposite of Pinecone. Cost-wise, the software is free, but you pay for the high-RAM hardware and potentially the companion database. The effort is intermediate, easy to start locally, harder to scale robustly in production with metadata.
Right, FAISS is the high-performance open source library, good for speed if you manage the memory and metadata yourself. What's the story with pgvector?
pgvector is another open source option, but it's an extension for PostgreSQL, the very popular relational database. Its biggest advantage is integration. If you're already using PostgreSQL, you can just add this extension, add a vector column to your existing tables, and start doing vector searches alongside your regular SQL queries. That's super convenient. The setup can be a bit more involved than Pinecone, requiring some SQL knowledge to create indexes and run queries using functions like cosine distance. Like FAISS, lower distance scores typically mean higher similarity. Costs can be quite low, potentially the lowest if you already have a PostgreSQL instance. If you need a new managed Postgres instance, like from AWS or Google Cloud, a small one might cost $20, $40 a month, maybe half or a third of Pinecone's cost for a similar scale initially. So cost is low to intermediate. Effort is also intermediate, as it requires more database know-how than a fully managed service.
That's a great comparison. So Pinecone for ease in managed scaling, FAISS for raw speed if you handle the infrastructure, and pgvector for integration if you're already in the Postgres ecosystem. Well, we've certainly covered a lot of ground today. From the fundamental idea of turning data into meaningful numbers with embeddings, to storing and searching those numbers efficiently with vector databases, and finally seeing how this powers advanced AI applications like retrieval-augmented generation, even for complex data like video, it really feels like the plumbing underneath so much of modern AI.
It really is foundational, and the key takeaway, I think, is that the best approach, the right embedding model, the right vector database, the right RG strategy, it always comes back to your specific needs. What kind of data do you have? How much of it? What's your budget? What are your performance requirements? What's your team's expertise? There's no single right answer. It's about finding the right trade-offs for your particular situation.
Absolutely. And thinking bigger picture, this ability for AI to retrieve and integrate specific current knowledge from almost any data source, text, images, audio, videos, drawing, it feels like it's just starting to unlock new possibilities. We talked about chatbots and video search, but imagine truly personalized education where AI tutors can draw instantly from textbooks, lectures, and supplementary materials, or scientific research where hypotheses can be checked against vast multimodal data sets in seconds. It makes you wonder, what untapped knowledge is currently locked away in unstructured data all around us? What data do you, listening now, have in your organization or your personal archives that could suddenly become interactive and searchable using these techniques?
That's the really exciting frontier. We've built the tools to understand and retrieve information like never before. Now it's about applying them creatively to unlock all that hidden value.
A fascinating thought to end on. We hope this deep dive has given you a clearer understanding of these crucial technologies. Thanks for joining us on the deep dive.